This is a demonstration of a 4-bit binary ripple carry adder-subtractor that I built out of NEX. As you can see, it's a very big machine, about 78 inches tall. And basically this is a mechanical calculator that can add numbers together or subtract one number from another. And it's powered entirely by gravity, and it's made entirely of standard plastic NEX parts. So it works via these falling balls. You can see up at the top, I've already primed the 9 balls required for one operation. And when I pull the lever, they're going to fall all the way through the mechanism down to the bottom, and we'll see a 5-bit binary answer in these 5 slots down here. And just below the balls, we have where we set the input. There are 2 rows of 4 dials, and those are the 2 4-bit binary numbers that we're adding or subtracting. So every dial represents 1 bit of the number. If it's to the left, it's a 1. If it's to the right, it's a 0. So currently I have the top input set to 1101, which is 13 in binary, and the bottom is 0110, which is 6 in binary. And then finally we have the type of operation, either plus when this slider is pushed to the left, or minus, we have a minus sign when it's pushed to the right. But I'll keep that to the left. So the operation I'm doing is 13 plus 6. So at the bottom, we should end up with 19 in binary, which is going to be 10011, or ball, no ball, no ball, ball, ball. And there we go, it worked as expected. We've got 10011, which is 19, which is 13 plus 6. And you may notice that all of the unused balls went into this handy little basket. So here's another test. This time I'll show subtraction. I've got my basket of balls right here, and to reload the machine, I just have to manually grab them and put them in all the 9 slots at the top. And this is the part that I really wish was more automated. I have been thinking about making a chain-driven ball lift that brings the balls up automatically, but that's a lot of work to engineer, so I haven't done that yet. But there we go, it's ready to do another operation. And I've still got the dials set to 13 and 6, but this time we'll do subtraction, so 13 minus 6. But before I let this go, I want to mention a small caveat about how 2's complement math works in binary with subtraction. And that's that, well, at the bottom we have 5 outputs, 5 bits, and that's useful in addition mode because the leftmost bit is the 16s place. But in subtraction mode, that leftmost bit has no such significance. So really, whenever you're subtracting with this machine, you want to completely ignore whatever comes out of the leftmost bit. So we're doing 13 minus 6, which is 7. So the right bits should be 7 in binary, so it should be 0, 1, 1, 1. Ignore whatever comes out here. And there we go. As expected, we got 0, 1, 1, 1 in the right bits. And if you're savvy with your 2's complement math, you may realize that what I really did was -3 minus 6, which is 9, but that overflows to 7 down at the bottom. So now I'll just do a couple more demonstrations at a couple different camera angles. So this time, let's do 15 plus 15, which is the maximum possible. So all the bits are set to the left. And at the bottom we get 11110, which is 30, or 15 plus 15 as expected. And here I'll do 15 minus 15, so we put that in subtraction mode, and we should get 0 on the bottom. And since we were subtracting, ignore that bit, but we did get 0 in all the other bits because 15 minus 15 is obviously 0. Also, this machine can definitely do a smaller number minus a bigger number. You just have to be careful about how you read the output. So I have this set up to be 1 minus 2, which is going to be -1. So let's see how that works. So at the bottom, we ended up with 1, 1, 1, 1, which might look like 15, but if you read that as a 4-bit 2's complement number, that is in fact -1. And finally, I'll do 0 plus 0. So I've got all the dials pointed to the right, so everything is zeroed. But I'll film this one from the back side. And since we're doing 0 plus 0, the answer will just be 0. So there's going to be no balls in the front input. So we should end up with all 9 balls in the discard basket right there. And there we go. All 9 balls right there. Nothing on the output. So to explain a little bit about how this machine works, I've got this full adder module right here, and the big machine is effectively made up of 4 full adders, plus all the other parts that keep all the balls in place, and of course plus some stuff at the top and the bottom to handle input and output. And you can recognize the full adders on the big machine by noticing this distinctive tilting mechanism right there. That's the same exact thing as what we have right here. So right about there is one of the full adders, and there's another one right there, and also down there and down there. So this machine has 4 full adders because it's a 4-bit adder-subtractor. And in fact, the cool thing is that this is a very modular system using these full adder modules. So if I had wanted to, I could have made this into a 5-bit adder-subtractor by just adding another full adder right about there and then moving the input up by about a foot, because they do need to be stacked on top of each other, and that's why this machine is so tall. And in fact, I don't even know if I have enough K'NEX pieces to do that or enough ceiling space, but in theory, you can make this into a 5-bit or 6-bit or even like 8-bit adder-subtractor if you have the parts. So the full adder has 2 inputs up at the top. On the left, there's this gray piece, which indicates that's the 0 input. And on the right, orange indicates that's the 1 input. And there's 2 important outputs, the sum and the carry. And also in this demo version, there's this large trough, which is just kind of the discard area for all the other outputs because they don't matter here. But in the actual build, when you implement this, some of those do matter. And really, a lot of the pieces of this build are just making sure all the balls go into the right places. Whereas the majority of the logic is just done by these 2 moving parts, the tilter in the full adder and also this little lever right here. So what a full adder does is it simply adds 3 single-bit binary numbers together. So we have A, B, and C. All of them are either 0 or 1, and we want to add them together. And you might think that there are 8 ways that you could do that, but really, since addition is commutative, so like 0 plus 0 plus 1 is the same as 0 plus 1 plus 0, the order doesn't matter. So there are only 4 ways or 4 combinations for A, B, and C that you need to worry about as input to the full adder, and my design takes really good advantage of that. So for example, if we want to add 0 plus 1 plus 1, well, that's just 2, and 2 as a 2-bit binary number, which is our output, is 1, 0. And that 2-bit binary number ends up as the bits of the sum and the carry. And that's exactly what we have labeled here. And those are the important outputs because the sum is the value that actually rolls down the front here and ends up being displayed on the final output. And the carry is the real reason why the machine is so tall, because the carry from one full adder needs to go into the input of the full adder below it. So it needs to be physically above it. So, the height of this full adder is kind of the limiting factor on how tall the machine is going to be. So to show and explain how the full adder works, I'll just run through this table of values here, starting with 0, 0, 0. So that's gray, gray, gray. And you'll notice that the tilting mechanism is weighted so that it only tilts fully when exactly 3 balls are on it. So that's the way you make sure that you wait for all 3 inputs. And so for 0, 0, 0, we did indeed get a sum of 0 and a carry of 0 as expected. So that works. And now I'll do the next line, 0, 0, 1. But I can do this in any orders because the order shouldn't matter. So I could do 1, 0, 0. And that works because the tilting mechanism has this slight slope towards the center. So 1, 0, 0 is going to look the same to the tilter as 0, 0, 1 or even 0, 1, 0. So as expected, we got a carry of 0 and a sum of 0, or sorry, sum of 1 for 0, 0, 1. Next up is 0, 1, 1. And again, I could do it in whatever order. So I could do 1, 0, 1. And we should end up with a carry of 1 and a sum of 0. So that looks good. And then finally, we'll do 1, 1, 1. Which should give a carry of 1 and a sum of 1. And all of these balls are just discarded. They don't matter. So before I finish here, I want to point out the important internal lever mechanism of the full adder. That's this bit right here, because what it does is whenever a ball rolls down the center, either on this side or on this side, it tilts the lever one way or the other because the ball rolls down right there, tilting it like that or tilting it like that. And what that does is change the direction the 2 center balls roll because it has these little orange ramps right there and there. And importantly, we have these 3 red pieces which form a delay mechanism for the 2 center balls to make sure that they go down after the lever has tilted. So I can demonstrate this with 0, 0, 1. You'll see that the leftmost ball is going to tilt the lever and make sure that these balls roll to their appropriate places. The left are both discarded, so that doesn't really matter, but the right one came out here as the sum. So this ends the demo of my 4-bit ripple carry adder-subtractor made with NEX. I really hope you guys enjoyed this video, and this is in fact the very first video I'm putting on this channel, so I'd welcome any type of feedback, either a like or a dislike if that's really the way you feel, and especially I'd like comments because I'd love to hear what people have to say about what I've done. And also, if anyone is interested in seeing more details about how this works or just seeing me build these things in real time, you can check out my Twitch channel where I plan to stream myself making NEX contraptions like this and probably updating this build a little bit. You can check out the link in the description, twitch.tv/discretegames for that. And also I'll have some other links to the math and computer science topics I talked about today, like 2's complement and what a full adder is and ripple carry adders in general. So check the description for all of those links. And thanks again for watching. Have a great day.